In this video, we will discuss the probability behind mutually exclusive outcomes. We only have 3 learning objectives. The first, understand when 2 outcomes are mutually exclusive. That one's basically just the vocabulary. What mutually exclusive means, it's very straightforward. The second is to understand the concept of unions and intersections. Understanding unions and intersections requires us to be able to do work with Venn diagrams, and there are union and intersection symbols that we will look at for them as well. But altogether, the whole point for why we're doing these pieces is so that we can compute probabilities using a Venn diagram to get the answer, or using a formula to get the answer. Now, the major topic behind mutually exclusive outcomes is the idea that sometimes 2 events could never happen at the same time. And the example I picked here is one outcome is you're born with 5 fingers on your left hand. Well, another outcome is that you could have a genetic defect and then have 7 fingers on your left hand. Is it possible to have both exactly 5 and exactly 7 fingers on the same hand at the same time? Of course not. That would be an example of mutually exclusive outcomes. They just can't happen at the same time. Well, that's our primary vocabulary. Mutually exclusive, which is also called disjoint. Knowing that one vocabulary is the basis behind our first learning objective. Mutually exclusive means impossible at the same time. If it's not mutually exclusive, then it's not impossible. Well, this is a formula that you will want to have written down because it serves as one of the huge parts that we're going to be able to do, that we will do. In order to calculate probabilities, we'll use this formula. I suggest you pause the video to write down some notes. Did you notice that this symbol was used in the formula for mutually exclusive? Well, this symbol that looks kind of like an upside down U means union. Whenever you see this upside down U symbol for union, it means the first thing could happen, or the second thing could happen, or they could both happen at the same time. Any one of these possible things is used for a union. Basically, when you see this symbol U for union, your brain should be thinking of it as an or. And it's not like in English where it's pizza or chicken. You could have both. This symbol does mean both is okay. Well, please note, this piece of union ties back into our learning objectives. Understand the concept of a union. You should understand that this symbol for union means A or B or both. That's part of our learning objective. All right, so let's look at this one. The probability of a single die is rolled 1 time. What is the probability of getting either an even number or a 3? Alternatively, we could write this as even union 3. They mean the same thing. Well, for this particular instance, what is the sample space of rolling the die? What could you possibly get? 1, 2, 3, 4, 5, 6. So probability is number of successes over number of outcomes. How many successes do we have for even or 3? Well, those are the evens, or 3. That gives us 4 successes out of 6 possibilities. Our probability is 2/3. Second example, you draw a single card from a standard deck. What's the probability that you get a red card or spade? So it's probability of red union spade, which is the exact same thing as saying probability red or spade. So how many successes are there? How many reds are there? Okay, we've got 13 diamonds, 13 hearts for a total of 26 reds, plus 13 spades. That gives us a total of 39 successes out of the standard 52. And we know we could divide that by 13 to get the reduced probability 3 out of 4. Please note, though, that these are mutually exclusive events. Could you have a card that is both red and a spade? No. All the spades are blacks. So you can't be both at the same time. Because it's impossible to be both red and spade, that's what makes them mutually exclusive. In the last example, could you be both even and 3? No. 3 is an odd number, not an even number. Those could not be happening at the same time. Because they can't be happening at the same time, that's mutually exclusive. But we know not everything is mutually exclusive. It is possible for two outcomes to happen at the same time. For example, what's the probability that your mom is called Kelly? Or the probability that your dad is... Man, I can't even write the word dad. That's terrible. Well, is it possible to have that happen at the same time? Could you have both a mom named Kelly and a dad named Tom? Yeah. That's not my parents. So mine, if we picked my parents, that would be a failure. But it is possible somebody out there could have parents named Tom and Kelly. So, yes, this would fail to be mutually exclusive. This is not mutually exclusive. Okay, before we continue, I want to ask a quick question. Do you remember working with Venn diagrams? We were using them back in before. It's a very helpful tool to see how events and how outcomes are related. If you can draw a Venn diagram and be able to work with them like we had done before, it'll make a lot of our work easier today. In terms of Venn diagrams, these are the pictures. If you have mutually exclusive, which is also called disjoint, the inside circles will not intersect. They've got to stay completely separated because there's no overlapping part. Remember, mutually exclusive means they cannot happen at the same time, so you cannot be both. Well, if both is impossible, they should stay separated. So we have not mutually.
Simon's going to want to
Diagram winds up having a shared piece like this. Overlapping area that does intersect, not mutually exclusive. Here's the formula. You should pause the video, write down this one. This is for non-mutually exclusive. So this is a formula that we will need to use when we have problems that it is possible to have them happen at the same time. Once again, please note that we have the union symbol for or, but then we have this upside down U. It's a new symbol for us. That upside down U means intersection. You can almost think of intersection as an and, as the word and. Whenever you see this upside down U that means intersection, it tells you A must happen, B must happen, and more importantly, both of them, A and B, must happen at the same time. I want to remind you, This connects back to one of our learning objectives. The second learning objective is to understand the concept of a union and an intersection. Union means A can happen, B can happen, or both. Intersection means not they might happen, they must happen at the same time. That's our intersection. Intersection basically means and. In terms of the way things would look, how would we need to have these pieces shaded in? I'm starting off, you'll note on the left, this was the mutually exclusive. The right-hand side is not mutually exclusive. Just reminding you of what those pieces are. What I'd like to do is take a Venn diagram and start shading in the pieces that fit the union. What would the union look like for these pieces? Remember, union means A or B or both. Well, if we were going to shade them in, we could say, here's A or B or both. Where is the both? There isn't one. For mutually exclusive, there isn't a both. What about on the right-hand side? We would have A or B or both. In any part of those, we would have the union. What about intersection? Intersection means it must be A, it must be B, and it must be at the same time. Well, it's pretty easy to get, here's A, here's B, but where is the both? On this left-hand side with mutually exclusive, where is the both? There isn't any. A intersect B when you have mutually exclusive doesn't exist. It's empty. There is no overlap, so there is no intersection. But this is exactly why we call it an intersection. When we have not exclusive events, we'd have our A, we have the B, but where do those pictures intersect to give us the intersection? It's the overlap. This section here in the yellow is A intersect B. Here's our next example. We'll take a single 6-sided die and roll it one time. Let's suppose that the outcomes we're interested in are getting an even number and getting a number that's bigger than 3. Over here in the red is our sample space. So let's draw a Venn diagram for this particular situation. Well, we'll start off. We need to make sure that we have all of our sample space included. Well, what are the events that we're interested in? We're interested in getting even. We're also interested in getting bigger than 3. Is it possible for them to be both? Yeah, you have even numbers that are bigger than 3. That tells us they're not mutually exclusive. And so let's start filling in the information. Where is a 1 going to go? Is 1 even? Is 1 bigger than 3? No, so it has to go outside both circles. What about 2? 2 is even. Is it also bigger than 3? So it has to be inside the even circle, but not inside the 3 circle. What about a 3? Is it even? Is it bigger than 3? So it's got to be outside. 4. It's both. Since it's both, it's got to go in this tiny little overlapping section. What about 5? It's greater than 3, but it's not even. So we can have 5 inside the bigger than 3 circle, but it's got to be outside the even circle. What about 6? It's both. There's our Venn diagram. We've accounted for all the possibilities, putting them in their correct locations. Here's a similar one. We'll roll the same die. 1, 2, 3, 4, 5, 6. Suppose the outcomes we are interested in are even and prime. Well, that tells us we need a circle for even. We need a circle for prime. And let's start running through our list. Where will 1 go? It's not a prime number. It's not an even number. So it's outside. What about 2? 2 is even. 2 is prime. So it's both. But what about 3? 3 is a prime number, but it's not even. What about 4? Even, but not a prime. It's not a prime because you could take 2 times 2. 5? That's a prime number. The only way you could try to split up 5 with whole numbers is 1 times 5. And 6 is even, but not prime, so here is our Venn diagram. This Venn diagram I'm actually going to take and copy because we can use it here. What is the probability? Oh. Okay, there, I can move it now. What is the probability of getting an even number or one that's larger than 3? Well, what do we wind up with? How many numbers are even or larger than 3? Well, we have even, 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 bigger than 3. How many numbers did we have that work? 4 out of 6. By looking at the Venn diagram, we can get our answer 2/3. But this is not the only way that we could have done it. Instead of using a Venn diagram, we could have used the formula. Are these mutually exclusive events? Is it possible to be both even and bigger than 3 at the same time? Yes, it's possible. Because this is not mutually exclusive, which formula should we use? It tells us the probability of A union B we can get by taking the probability of the first one, add up the probability of the second one, and if we were mutually exclusive, we'd be done right there. We could use that formula if it's mutually exclusive. Because it's not mutually exclusive, we have to subtract off this part. Remember, union basically means or, intersection means and. So to get the answer, which we already know is 2/3, what's the probability of getting an even number? Even numbers are on 3 out of 6. How many numbers are larger than 3? People are telling me 3. But how many of them are both even and bigger than 3? That's 2 of them. We have the 4 and we have the 6. Well, crunching our numbers then, 3 plus 3 subtract 2 gives us 4 out of 6. And we get the exact same answer that we had before. We could do it with a Venn diagram. We could do it by listing the sample space. We could do it by using a formula. We have multiple strategies. Okay, here's our problem. Suppose there is a 25% chance that it snows today. And there is a 75% chance that it will be over 50 degrees Fahrenheit. But there's also a 10% chance that it will be both snowing and over 50 degrees. What is the chance that it will neither snow nor be over 50? And this is one that you look at and it's a lot more complex than just rolling a die. It's not like we can say, oh, here's my list of 6 outcomes and then just pick. Let's create a Venn diagram for the situation. What are the things that we're looking at? Well, it might snow. So we'll put in a circle for snowing. What's the probability that it's going to snow? Probability that it snows is 25%. That tells us if we add up everything inside, it's got to be a grand total of 25 inside this circle. But what else could possibly happen? Well, it's the other event we're looking at is that it's warmer than 50 degrees. So here's our greater than 50 degrees circle. And what's the probability that it's going to be warmer than 50? That's 75%. What about the intersection? Intersection is 10%, so we could go through and say, here's 10%. Add up the numbers, what do you get? Is it possible for a probability to be greater than that big? No, the maximum probability, a sure thing, is 100%, so this is telling us that there's something wrong. The something wrong is the fact that we're including pieces that we already have. 25% comes from the fact that the entire circle for snow, the whole thing, everything inside it, needs to add up to 25%. But we don't have that. Ours adds up to 35. That's a piece that we need to fix. Instead of coming back and saying that the whole piece was 25, we know that this piece, the overlap, is 10%. So if 10% is already accounted for, what's the rest? 25 minus 10 gives us 15%. And we will need to do the same thing for the over 50 degrees. The probability that you get over 50 degrees is a grand total of 75. Well, if it's over 75, if it's 75%, that means the entire circle needs to be 75. But we've already used the 10, so if we need 75 and we've used 10, how much is left? That's 65%. Now add up the 3 numbers. How much total do we have so far? 15 plus 10 plus 65. That adds up to 90%. But what is the grand total for absolutely everything? Everything's 100%. So there's still an additional 10% not accounted for. That last 10% to get us up to 100, that's the outside stuff. That whole piece is creating our Venn diagram. Now that we have the Venn diagram picked, what is the probability that will be not snow and not over 50? Well, where's that part on our Venn diagram? Not snow and not over 50 has to be inside both circles. That's this region. So what percent is that? 10%. And a Venn diagram was a completely valid strategy to get that answer. A lot of people really like Venn diagrams, and it's just because they like to have the picture that they can look at, it's very effective for them. Not everybody, though. A lot of people don't like the Venn diagram because of the amount of work it takes. You have to spend a lot of time thinking through and making sure all the sections are filled in correctly. And if you make a mistake, it causes big problems. Some people don't like working with Venn diagrams. That's why we also have our formula. But we have to make sure that we're using the correct formula. Were these mutually exclusive events or not? Yeah, we had the overlap. Because we had the overlap, they're not mutually exclusive, which tells us that we need to use this formula. Probability of A or B, probability of A plus the probability of B, subtract off the probability of both. Well, which pieces do we know? What's the probability of getting A is snow? Okay, so if we're saying A right here is not snow, what's the probability of getting not snow? Or we could, people are looking a little bit confused, so let me rewrite this a little bit. A is the probability that we get snow. B is getting 50 degrees or more. What's the probability of A then? That's the probability of getting our snow, which we were told right here. There's a 25% chance that we get snow. So our first number is 25. Got it. What about the next part, the probability of B? That's the probability that we get over 50 degrees. And Ian, you told me that right there, it's 75. Then we have to subtract off the probability of being both. What is the probability of it being both? That was 10%, so subtract off 10. And we wind up getting this answer, 25 plus 75 minus 10 is 90. It says the probability of getting snow or over 50 degrees is 90%. The problem that we asked, though, what is the probability that there's no snow and not over 50? That's just the complement. It's saying, what's the exact opposite? Well, if we're looking exact opposite, we know if we have 100% minus the probability of the complement, that's just going to be our probability. Or in this particular instance, we could also have it sitting right here. If we subtract off, man, my handwriting is terrible today. If we took 100 and minus off the probability, we get the probability of it being the other one. Well, the short version behind that is 100 minus the 90 gives us our 10% that we were looking for. Some people prefer to use the formula just because it's an equation and they like algebra a little bit better. If you don't mind doing some substitution and some basic algebra, the formula is a good strategy to use. Okay, so which of these events are mutually exclusive? Remember, what does mutually exclusive mean? Mutually exclusive means it's impossible to happen at the same time. So for part A, you go to the pet store to buy a pet. You buy something with legs. Option B, you buy something that has scales. Could you have that happen at the same time? Well, is there a pet that you can have legs and has scales? Yeah, you've got lizards. Lizards are both. Lizards are, man, this thing hates me. Lizards are both. There we go. Because lizards are both, that tells us this one is not mutually exclusive. What about B? You order a pizza. Option or outcome A, you order something with sausage. Outcome B, you order something with pepperoni. Is it possible to have both at the same time? Yeah, what about lover's pizza? What about just a plain sausage pepperoni pizza? Because it's possible to get both at the same time, this one is not mutually exclusive. Problem C, you pick a prom date. Outcome A, your date has a pulse. Outcome B, your date is an inflatable woman. Is it possible to have both at the same time? Something with a pulse and an inflatable woman? Yeah, the inflatable woman doesn't have a pulse. Because you cannot have both at the same time, this one actually is mutually exclusive. Radio stations have four-letter names like KMHA. You decide to pick a radio station to listen to. Outcome A, the first letter of it starts with a W. Option B, it starts with a K. Could you have both? No, it's the first letter. This is one that is mutually exclusive also. Being able to identify if it's mutually exclusive is important because it changes the formula. It's like when we were looking back at combinations and permutations. If you pick the wrong formula, you get the wrong answer, even if your number crunching is correct. It was the same thing when we had independent or dependent events. They have different formulas. If you pick the wrong vocabulary, you wind up with the wrong formula and therefore the wrong answer. Even if your number crunching is good, you have to make sure you're starting off with the right equation to use, and the right equation is based off of identifying, is it mutually exclusive, yes or no? Those play a role because our learning objectives, you need to be able to understand when two outcomes are mutually exclusive. That's what we were just looking at. Because along the way, you'll be using the intersections and unions inside the formula. The formulas are the last part. You can use a Venn diagram for a picture, or you could use one of these two formulas, whether mutually exclusive or not mutually exclusive. You'll have to make sure you're using the right one. Okay, here's our last problem. Rock of Ages in Las Vegas has 50 musicians who can play the guitar, whether it's bass guitar, lead guitar, or rhythm guitar. But being that they're professional musicians, a lot of them will play more than one type. So, we're given a bunch of situations, and at the end it says, draw a Venn diagram to determine how many can play lead guitar only. What is this going to look like? Well, we have our overall piece. Here's everything. The three possibilities that we have, oh, put that over here. This could be our circle for lead guitar. This could be our circle for bass guitar, and then we could have another circle for rhythm guitar. But we've got to make sure that we get them oriented in such a way that they all fit. And so this is what we wind up with. And I'm going to have to shrink the size of this thing down a bit. It's too big. Okay, shrink the size of this one down a bit. And shrink the size of this one down. Okay, so there we go. This one is the lead guitar. This is the bass guitar. And down here we'll have the rhythm guitar. Let's start filling in the pieces that we know. 12 people can play all three types. Where does that go? It's got to be in the intersection of all three circles. So where is the part that has all three? That's this region here. We've got to have 12 filled in. Go to the next one. 14 can play both rhythm and bass, but not lead. So which section has rhythm, bass, but not lead? Okay, people are pointing and saying here. This section is rhythm and bass, but it's still outside the lead guitar, so we've got 14 there. What about 10 people, lead or rhythm, not bass? That's here. Lead and rhythm. It's in both circles, but still outside the bass one, so that gives us 10 in this region. And we can continue and get 2 people play bass or lead, but not rhythm. Well, that's this tiny little area up there. And then when we continue, we get 5 musicians are bass only. So that's here, because it's outside the other 2 circles. And then we could say 4 are rhythm only, which would be down here. And then what's left? The only part we have not filled in is the lead only. And I'll do that one in this, I'll go with this teal color. So how many are only lead? Well, here's the big part. We know that there are a total of 50 people. So when we add up all these sections that don't overlap, the total number has to be 50. Let's start adding up the pieces that we have. 12 plus 14 plus that 10, 5, 4, and the 2. If we add them all up, we'll get how many people we've already accounted for. So 2, 4, 2 plus 4 is 6, 11, 15, 17, which adds up to a grand total of 47. So if we already have 47 people, how many are left? 3. How many people play lead guitar only? We got our answer. Using a Venn diagram like this is very, very helpful if you've got really complex problems like this. The Venn diagram is just one strategy that we have. We would be able to compute probabilities based off that Venn diagram. But we can also use pieces like here, where, come on, where is it? Where is it? Okay, this one. We would be able to get them with probability. We could calculate probability using a Venn diagram, or we could use it with the formula. Please note our 3 learning objectives. Can you identify when 2 outcomes are mutually exclusive? It's just vocabulary. Is it possible to happen at the same time, yes or no? Secondly, do you understand the concept of a union or intersection? Unions mean or, intersections mean and, where you must have both at the same time. And then lastly, could you create Venn diagrams or use formulas to crunch the numbers and actually get answers for probability? That's the 3 things that we were hoping to be able to get out of this particular section. If you've got it, you're good to go.